Okie dokie, continuing the exponential functions more practice worksheet. I'm on number 9, and I'm going to try to get through 13 on this video. It says that we have $500 in our account. If someone has $500 after 4 years. Okay, so something's happened, the money has gained interest, and at the end of the 4 years, we have 500. So if we look at our interest equation, that would be A. If we look in our y equals ab to the x equation up here, then this would be y. It's the final result, the output. 4 years, that's going to be our t value. The rate, 2.5% written as a decimal is 0.025. So you're going to divide 2.5 by 100 because that's what a percent means, out of 100. How much money did I start with? So what are they asking us for? They're asking us for the principal. So we're going to write this kind of the way we've written the other equations, and I want to show you how the ab to the x thing plays into this, the general form for an exponential. So we have 1 plus, we know that in our interest equation we would have the 1 plus r over n to the nt would go here. So our rate, 0.025, divided by n. Okay, well, how often are we compounding this? It says 2.5% per year. So it's only a yearly thing. So n in this case would be 1 for 4 years. So we can kind of generalize this a little bit. P times 1 plus our rate, 0.025 to the 4th. So this n here and this n here kind of go away. And you basically end up with the form y equals a times b to the x, where b is either 1 plus the rate of growth or 1 minus the rate of decay. How much are you losing per year if it's like a car value that's depreciating, or how much are you gaining per year like this interest rate. So you are going to basically get one number for this 1.025 to the 4th, and that number is 1.104. And you will find that the principal is equal to $452.98. Which is a great amount to throw in the bank. Some people do 450, but 452.98. All right, number 11. We've got a population that's growing here of a city, and it says the population in 1990 was 400,000. What would be the predicted current population? And then another question, in what year would we predict the population to be 1 million? So current population, let's kind of put an equation together here first. So 5% is our rate, so and its growth, so we would have 1.1 plus 0.05. You can write that just as 1.05 if you want. And it's going yearly, so we're trying to find the current population. So right now, I think it's 2020, if you're watching this video now. So that would be 30 years from now. So a 5% growth for 30 straight years. And what do we start with? We start with 400,000, and we're going to find out the amount that we have at the end of that. For this, I got that the amount is 1.73 million. Okay, so that's a lot of people, depending on where you are. Okay, so it's going to take us 30 years to get 1.73 million, so I'm betting that it won't take 30 years for us to get to 1 million. So how do we find that out? Well, we know the amount now. What do we not know? We don't know what year. That's t equals question mark. You can't find what you want to find unless you know what you want to find. Okay, so you have to know that you're looking for t. You could also just start plugging in all your unknowns, and eventually you would get to t and be like, oh, hey, I don't know that. Okay, so then how are we going to solve this? We're going to divide both sides by 400,000. We get 2.5 equals 1 plus 0.05 to the t. And we've talked about new ways to solve this, and so I'm going to use one of those new ways. You can put both of these things into the calculator, 2.05 and y1, so you're going to graph both of them, and 1.05 to the t, graph them both, find the intersection, and you'll find out the time. But what we've talked about is that you can take the log of both sides, and what does that do? It takes the t and it brings it down, so it takes that t out of the exponent. You end up with t times the log of 1.05 is equal to the log of 2.5. Then you divide by those. So logs are super awesome because they take things out of exponents, which is a problem for us algebraically. When you do log of 2.5 divided by the log of 1.05, you get 18.78 years. So that's the answer to the second part of this question. Could have found the same thing graphically. I think we did that one in class. Okay, let's jump to the last one. A little bit tricky. Number 13. This strain of bacteria that's doubling every 5 minutes. And I'm going to do something with this that it's limited enough that I think we can do it in this form here. I'm going to make a table. Fictional strain of bacteria doubles every 5 minutes. Okay? So at minute 0, we are putting in this single bacterium into a bottle. One of them. And then, let's do 3. I'm running out of room. Hopefully that'll do it for me. It's not gonna. Okay, so 5 minutes later, I'm gonna write in the actual time. So this is 9 o'clock. At 9:05, what happens? We double. Okay? So think about these things splitting. We had 1, now kaboom, we have 2. Not really a problem for us yet, or so we think. So what happens at 9:10? They're going to double again to go to 4. 9:15, what happens? They double again to go to 8. If you play the game 2048, this is looking familiar to you. 9:20, we're going to have 16. 9:25, 30. Then we'll go to 32 when we double again. Then we'll go to 64, we'll double again. At 9:35, we have our some kind of split. I think our 7th, we end up with 128. 9:40, we'll end up with 256. 9:45, we end up with 512. 9:50, we end up with 1,024. 9:55, we end up with 2048, and you won the game. And then what happens at 10 o'clock? We go to 4,096. Okay, so what is important about this 10 o'clock? 10 o'clock, we are exactly full. Exactly full. And what does it ask us? At what time was the bottle half full? So let's look at our chart, see when we're half full. So if we're full at 4,096, how many bacteria would fill, or half fill, the bottle? Probably half that much. Well, where do we have half that much? At 9:55. Just 5 minutes ago, we had half of the total amount that was going to fill the bottle. And also, this problem is difficult, especially if you try to set it up as an exponential function. You end up doing a lot of unnecessary work there, because what this question is more about is understanding how an exponential function works. I mean, look at this area right here. If you think in terms of bacteria, this probably isn't a big deal for you. The first 40 minutes, that thing's just incubating in your system. Then it starts to pose a problem. So exponential functions, if you look at them on graphs, like we have on this worksheet in number 3 and number 4, you see things that look like this. Okay? So right here, the rate of change isn't very big. But up here, big numbers, when they double, they get really big really fast. Okay, so the first part, slow growth, and then boom, that's when things go viral. All right, so the answer to this one is 9:55. So just 5 minutes ago, the thing was half full.